Welcome to our video and slide presentation for Experiment 6, Thin Layer Chromatography. We are from Lecturer Group 3, Subgroup 1. Our group members are Esther Yin Hei, Chong Charlie Wen, Fernando and Evangeline Daphne Anat Davis. The objectives of our experiments are to investigate the effect of different solvent systems on thin layer chromatography separation, to understand the theory and principles behind thin layer chromatography, and to perform thin layer chromatography on dye samples and observe differences in their separation and movement. What is actually chromatography? Chromatography is a technique used to separate the components in a mixture. Components distributed between the mobile phase, which is the liquid solvent, and the stationary phase, which is the solid medium. What is thin layer chromatography? Thin layer chromatography, or TLC, is one of the chromatographic separation techniques. It is an analytical method used to separate and analyze the components of a mixture. TLC is commonly used to determine the number of components present in a sample, to identify compounds, and assess purity. Next, let's learn more about the TLC plate. A TLC plate consists of a sheet of glass or plastic coated with a thin layer of silica gel or alumina which serve as a stationary phase. Silica gel contains many hydroxyl groups on its surface, making it highly polar. These polar surfaces interact strongly with polar compounds through absorption and hydrogen bonding. As a result, polar compounds interact more strongly with stationary phase and therefore move more slowly up to the plate. Less polar compounds interact less strongly with the stationary phase and move faster and further with the solvent. The difference in movement allows the component of a mixture to be separated and analyzed.
First, for our apparatus, we use TLC slides, beakers, parafilm, a micropipette, a ruler, and a pencil. Next, our reagents include 3 indicator dyes: methyl red, cyanogen orange, and bromochloro green. We also use 4 organic solvents: acetone, ethyl acetate, hexane, and ethanol. For the procedure, Step 1, 6 beakers used as chromatography chambers are cleaned and dried. Step 2, mixtures of the solvents are prepared in the indicated volume proportions. Each mixture is transferred to a separated beaker covered with a parafilm and clearly labeled with its identity. Step 3, 6 TLC slides are prepared. Using a pencil, a line is marked lightly across both the top and bottom of the slide. As shown in the diagram, the development distance is 5 cm on a 7.5 cm slide. We must not mark too deeply or the silica coating will be removed. Step 4. 4 small pencil dots are marked on the baseline. Above the top line, they are labeled R for methyl red, X for cyanogen orange, G for bromochloro green, and M for the mixture. Step 5. Small samples of the dye solutions are obtained. Using a separate micropipette for each, a single small droplet of the dye of mixture is applied to its pencil spot, keeping the spot as small as possible. Step 6. The spots are allowed to dry. Then, the TLC slide is lowered gently, spots downward, into the solvent system. We take care not to weight the spots directly, leave the beaker undisturbed, and cover it tightly with parafilm. Step 7. The solvent is allowed to rise until it reaches the upper pencil line. The slide is removed, and the exact solvent front is marked quickly before it evaporates. The slide is labeled with its solvent system identity and set aside to dry completely. Step 8. The entire process is repeated using the additional TLC slides and remaining solvent system. Step 9. The RF value is determined for each dye in each solvent system and recorded, and the TLC slides are kept for the lab report.
Based on the results, acetone and ethyl acetate gave the most complete resolution of the 3 dyes. The RF values were 0.84 for methyl red, 0.24 for cyanogen orange, and 0.60 for bromochloro green. These values are clearly different from one another, showing that these dyes were successfully separated. This happened because the solvent mixture has balanced polarity, allowing each dye to interact differently with the silica gel stationary phase. On the other hand, ethyl acetate and hexane gave the poorest resolution. The RF values obtained were 0.79 for meteorate, while xylanol orange and bromocresol green both show 0.00. This means that some dyes did not move from the baseline, causing incomplete separation. The solvent system was likely too nonpolar, preventing effective movement of the polar dyes. Moving on to the calculation. The main calculation in this experiment is the retention factor, as known as RF value. RF values are used to identify unknown chemicals by comparing them to a range or a reference substances. The RF value for a particular substance will always be the same if the same solvent and stationary phase are used. The formula used is RF equals distance traveled by the spot divided by the distance traveled by the solvent front. For example, using the acetone and ethyl acetate solvent system, the solvent front traveled 8.00 centimeters. For methyl rate, RF equals 6.70 divided by 8.00, giving RF value of 0.84. For xylanol orange, RF equals to 2.30 divided by 8.00, giving 0.24. For bromocresol green, RF equals 4.80 divided by 8.00, giving 0.60. Different RF values show that these dyes travel different distance on the TLC plate.
So to begin with the discussions, I will first discuss about the theory behind the thin layer chromatography or TLC. So TLC is a technique used to separate and identify compounds in a mixture. So in this experiment, it was used to separate the three dyes, which is methyl red, xylanol orange, and bromocresol green. So the TLC systems consist of a stationary phase and a mobile phase. The stationary phase is the silica gel, which is polar, and the mobile phase is the solvent mixture that moves up the TLC plate. So the separation occurs because each dye interacts differently with the stationary and mobile phase. More polar compound will be more strongly attracted to the silica gel, so it will move more slowly and will have lower RF values. And in contrast, less polar compounds will less strongly attracted to the silica gel and will travel further up the plate, which results in higher RF values. And the RF values is an important measurement in TLC because it allows us to compare how far each compound travels and evaluate the effectiveness of the separation. Next, I will explain the interpretation of the result. So, ethyl acetate and hexane solvent system has shown poor separation. The methyl red has an RF value of 0.79, however both xylanol orange and bromocresol green had an RF values of 0. And the mixture spot had an RF values of 0.81, which is very close to methyl red, which indicates that the dyes may have overlapped and were not effectively separated. And this was likely due to the unbalanced polarity of the solvent system. And next, for the acetone and hexane solvent system, it gave us partial separation. Methyl red has an RF values of 0.95 and traveled close to the solvent front, while xylanol orange had an RF values of 0.07 and had remained near the baseline. Bromocresol green show intermediate movement with an RF values of 0.54. And although some separation has occurred, the mixture still overlapped with methyl red and indicated incomplete fixed solution. And finally, for the best separation is by acetone and ethyl acetate, and the RF values were 0.84 for methyl red and 0.24 for xylanol orange and 0.60 for bromocresol green. The distinct spots were observed on the TLC plate, showing clear separation of all three dyes. This solvent system provided a balanced polarity and allowed each dye to move according to its interaction with the silica gel. For the safety and suggestions, several precautions should be taken to ensure accurate results and safe laboratory practices. One important suggestion is to apply in small and concentrated sample spots, as large spots may spread during the development and could cause overlapping, which would make the results difficult to interpret. The solvent front should also be marked immediately after the TLC plate is removed from the chamber to ensure accurate RF calculations. And to prevent contaminations, a separate toothpick should be used for each dye solution. In addition, the TLC chamber should also remain covered throughout the experiment to reduce solvent evaporation and maintain a consistent development conditions. And from a safety perspective, the solvent used in this experiment are highly flammable, so that they should be handled in a well-ventilated area and away from open flames and heat sources. So in conclusion, the experiment has demonstrated that thin layer chromatography is an effective method for separating dye mixtures. The result has shown that the choice of solvent system also plays a major role in determining the quality of the separation. And different solvent systems produce different RF values because of the differences in polarity and interaction with the silica gel stationary phase. And among the solvent system tested, the acetone and ethyl acetate were the best separation, provided the best separation of the dyes, and while the others were not as effective. And overall, the experiment has successfully confirmed the fundamental principle of TLC, which more polar compounds travel shorter distances and have lower RF values, while less polar compounds travel further and have higher RF values. And that is all for me. Thank you.
Hi, my name is Chai Leven, matrix number 109287. Today, we are breaking down 3 critical questions from our TLC experiment to understand exactly why the procedure requires such precision. First, why must the sample spot applied to the TLC slide must be as small as possible? Think of it as a resolution problem. As the mobile phase travels upwards, sample spot naturally diffuse and spread out. If your initial spot is too large, the component form broad bands that smear and overlap. Keeping the spot small ensures a sharp, distinct separation so you can easily calculate accurate RF values. Next up, why cover the beaker with paraffin? This creates a sealed chamber to saturate the internal atmosphere with solvent vapors. If left open, the solvent evaporates straight off the surface of the rising plate. This evaporation forces the solvent front to move unevenly or stall out completely. Furthermore, in mixed solvent, the more volatile liquid evaporates faster, shifting your solvent ratio mid-test and ruining your result. Finally, let's talk solvent polarity. The question asks, does the polarity of the solvent mixture affect the completeness of our dye separation? Yes, heavily. TLC involves a constant push and pull between competing interactions. The stationary phase, the silica gel on the slide, is highly polar and will strongly absorb the dye molecule. If your solvent is too nonpolar like hexane, it won't be strong enough to pull the dye from the stationary phase, and the spot will stay stuck at the baseline. If the solvent is too polar, it will easily overcome the stationary phase grip, carrying all components straight up to the solvent front without separating them. By testing different mixtures, we look for an intermediate polarity. In our lab, acetone and ethyl acetate give the most complete resolution. It perfectly balanced the pool, allowing methyl red, bromocresol green, and xylanol orange to travel at distinctly different rates based on their unique molecular structure. Conversely, ethyl acetate and hexane give the poorest resolution, leaving components overlapping at the baseline.